Azcarraga for the project 2 of Automata Theory, Computability, Formal Languages, CSC 6115M, under Dr. Arnie Azcarraga. So this project 2 entails implementations of Turing modules and solving different problems. For this computer program, I have 3 sample programs. The swap program, it's the first one we're going to test. The n1 squared plus n2 squared program, that's the second problem. And the third problem is the n minus 1 program. So these are the Turing modules that's included in the said program for the swap. Swap n1 n2 with these Turing modules, the n1 squared plus n2 squared problem, and you'll see here in the notes the modules, Turing modules entailed for creating the program. And the last problem I used for testing, the n minus 1, which has these 11 Turing modules. So just to walk through on the Java classes, so I use the Java programming language to implement the Turing modules and to interpret the 3 different programs. So it starts with this main class Turing modules main, here where I define the input being the program, the actual program, which it looks like this on the right side of the screen, that has the actual program of the Turing modules and their arrangement, and the second input being the omega, or a text file that contains the input string that will be processed by the Turing modules program. So here you'll see that those are the 2 arguments that is being processed by this file utility class that will load all the omega lines, which means these input lines, and the program lines, which will read and parse all these program lines, the Turing modules. And this will just loop all the omega input from the text file, and will process and will instantiate this class called module processor that's instantiated here in line 16, and we'll call the process tape, which has this implementation. The process tape of module processor will just basically loop in to all the programs and call the module factory. So I implemented the factory design pattern in order for this module factory to return the corresponding Turing module implementation based on the input program. So the module factory just basically return an instance of the Turing modules. For example, here on the left side of the screen, you'll see all the Turing modules that is implemented. So we'll just basically return an instance of the Turing module based on the program that we are running. So we are now going to test running the first program, the swap program, for test 1. So you'll see here on the right side of the screen the actual swap Turing modules program. This part of the screen shows the test omega or input string or stimuli for the swap program, and this is the console, the bottom part of the screen where we will be displaying the result. I'm running now the program for the swap. Just scrolling up, so you'll see here this is just a display about the project, and omega 1 start indicates that this is the start of processing for the first input, or the first omega in the input file swap underscore omega dot text. And you'll see here the initial state of the tape, and this displays the cursor where it's indicating that the starting point of the cursor is in the first sharp of the omega. Here you'll see that the first program of the first Turing module is displayed shipwright 2, wherein you'll see that the cursor moved from here, from the first sharp to this part sharp, which represents that executed the module SHR2. The second step based on the swap program is copy 2, which means it's going to copy this part of the tape to this part and place the cursor here. Then ship left 2, which we will be moving the cursor from here to here. And then the last step or the last module for the swap program is move 1 2, which means we will be just targeting to erase this part of the tape and then retain this to complete the swap. So you'll see here the final output of the first omega. It's now 33322 from the initial state of 222323 as shown in this input text file as well. Now you'll see that this is the indicator that we've done processing the first omega, and this is now the start of processing the second stimuli. Now here we just, in the first example, we used real numbers, actual numbers for swapping N1 and 2. Now for the omega second input string, we use the symbol 1 only, N1 be having two 1 values and N2 having three 1 values. Now same steps, secure ship right 2. So this is the initial state of the, and this is the cursor, initial state of the tape. SHR2 happened and then it moved here, the cursor, copy 2, copy the value 1 1, and then shift left 2, we move the cursor from here to here, and then the final module move 1 2, erase 1 1, and then place the cursor here and retain 1 1 1 1 1, having the final state of this one, 1 1 1 sharp 1 1 from the initial state of 1 1 1 1 1, where we successfully swap the value of the N1 and N2. So for the second test program, we will be using the N1 squared plus N2 squared Turing modules. So here it entails 11 Turing modules to properly have the program of the N1 squared plus N2 squared. We will be testing, for simplicity, we will just be using simple or low value numbers to limit the output in the console screen. So I'll just clear the screen. We've already updated the input file for what program to use. This time this program, and the input file for the omega for this one. I'm running now the program for N1 squared plus N2 squared. Scrolling up, so still the same, just a display. This will display in every run that we will be doing. So here you'll see that this is the initial or the first omega in the input stream, 1 and 3. 1 and 3. So the first Turing module is ship right 2. So there, ship right 2, then copy 2. So it will copy the value 1. Copy 1, which will copy the value 1 again. And just keep placing the cursor on the right side after every copy. Then shift left 2. And then mult, which means we're gonna multiply this one value by this value, the two values that we previously copied, and we'll display the value here. Now we're gonna shift right 1 and then copy. So at this part we already did the N1 squared. This value already represents the N1 squared, since we also we executed the mult for these two inputs. Now we now have to move on to just display the how did we come up with the N2 squared. So here, after doing more on the N1 squared, we're now going to shift right 1 to place the cursor here, execute copy 2, so we'll copy the value 3 here, and then copy 1, which will copy again the value 3, and then shift left 2, so we can execute the Turing module for 3 and 3. So 3 times 3 is equal to 9. Therefore, we already have the value for the N2 squared. Now we're going to execute the shift left 1. So we can place the cursor here and do an add. So that's the part where we add the N1 squared plus N2 squared. which is equal to 10 based on the input. Now, all we have to do is to eliminate n1 and the initial values of n1 and 2 and keep the actual value for n1 squared plus n2 squared. So hence the Turing module move to 1, which has the output tape of this one. And that's the end for the first stimuli in our input string, 1 and 3 being n1 and n3 respectively. Now, for omega 2 on the same input file, 2 and 3. So it will just reuse the same, all these same 13 modules until it successfully computed the value for the n1 squared plus n2 squared. So here, same steps. So step 1, 2, 3, 4, mul n1 squared, copying, setting up the value for the n2 squared until you hit the add for the n1 plus n2, and the last module move to 1, which will keep the value of the computed value for n1 squared plus n2 squared here. And that's the end for the second omega for the n1 squared plus n2 squared. The last program that we will use for testing the computer program is the n-1 program. So I'll just update the, the parameters to point to the n-1 program and n-1 omega. So here is the n-1 nodes I have. So it contains 11 Turing modules, which corresponds to these Turing modules as our input program. And I'll be using these two input string, 2 and 3, as the omega for the program. I'm clearing the console. I'm running the application now for the n-1. Scrolling up, the same display, the start of omega 1 for the n-1 program, the initial state of the tape, given the value 2 here, which corresponds to this first line on our omega input file, and the initial placement of the cursor. Now, the first module is shift right 1, so it will just move the cursor from this point to this point of the tape. Now, issue the copy 1, which will copy the value 2 and paste the cursor here. Now, const 1 will put the value 1 here and keep the cursor at this point. The next module is shift left 1. Shift left 1, so we'll just move the cursor from this part to this part. Now, it's gonna do a checking of equal. So it's gonna now check after the shift left 1, it's gonna check whether the 2 and 1 are equal. If yes, it's going to step or module 11, which is the half, which means we've already reached 1. But in this case, it doesn't, because 2 is not equal to 1. Hence, we will just proceed to the next module. Sixth module, copy 1. We'll just put 1 here again. Shift left 1. We'll place the cursor here. Then we execute the monus, so we can have the difference between 2 and 1. And the difference will be here, the monus. Now, the 10th module is go to 1, which means we're gonna jump from the 10th module to first module again to repeat the process. So here you'll see here that the module 1 is displayed again, which will just repeat the whole process. So I'm just gonna jump on the part where it's gonna check again whether the values for checking the equality is already met. So here on the fifth module, if eq, this is 1 and 1, so we've reached the condition to be true. If equal, you jump to 11, the module 11, which is half. So you'll see here that right after the fifth module, the 11th module half is displayed, and which will display the final state of the tape. So this is the initial state of the tape. from the beginning of the processing for the first omega, and the end state of the tape is here for the n minus 1, n being 2. So you'll see that it's 2 and 1. And that's the end for processing the first input or first omega in this input text file. Now, the the last input or the second omega for the same n minus 1 program. So you'll see here the initial state. So we're just using 3 at this time as slightly bigger number, just to limit the display in the console. So same, we execute all the modules based on this input program until we reach the fifth module, if EQ. So it will compare whether 3 is equal to 1. If not, just proceed on step 6 until you reach 10, which will until you reach 10, which will go to back to the module 1 here. So it will just repeat the process until it displays all the valid values until you reach the final state, given the n being 3, and the final state would look like this: 3, 2, 1. And then it's gonna reach again the fifth module, which will compare that this is already equal. So it's gonna jump to the 11th module, the halt module, and will print the final state of the tape, which displays the correct values for the n minus 1 and being 3. So I'm just gonna quickly go through on how the program works. Again, I just instantiated a module Java class called modules processor. So this module processor is a generic processor, module processor, which implements a process tape. And this process tape is the one that's actually instantiating or using the module factory to return the module or the Turing module that I will be needing based on the input text file, and we'll just call the process tape module wherein I pass the tape and the program as the parameter. So this process tape module is actually an interface that is implemented by all the modules here, you'll see, and it will just return an int value, process return not equal. It will just return 0 and 1. So if it did not return 0, which it means that there's gonna be a looping or there's a part that you would need to jump from one module to another. Like for the last example, for the EQ, for the fifth module, that you need to go to module 11, and for the go to that you need to go back to 1. So that's how I handle it, the looping. So if you look at the implementation of that EQ and go to, it's gonna look like there. So go to T, so it will just return X, X being the value with the parsed value inside the parentheses for the module go to T. So X here is actually the T here. Now for the EQ, if EQ, if EQ, so it will return X here, which is the parsed value of the value inside the parentheses for the EQ module. And if it's not if the n1 and n2 is not yet equal, it will just return 0, which means you just have to go to the next module. So you'll see here all the implemented Turing modules and the tape. So I used object-oriented programming design to define the tape, given that the tape has 3 attributes: cursor, the initial value where the cursor is placed to display, just like this one, and then omega, which represents the string from the defined omega input text file, and the program as the list of string, which represents this Turing module program. And these are just getters and setters. And this is an internal function for printing the pointer. So that's how I'm printing the cursor or the placement of the cursor. I always update this cursor int value of the tape object, so I always know or keep the track of the position of the pointer. That's it.